Our group is comprised of Ashley Brown, James Brown, Andrew Mortimer, Cee-Jay, Sach, and Grace Williams, and today we'll be discussing our experiment, rainfall frequency and erosion rates in Pilbara soils. I'll be giving an introduction and the aims of the experiment. Grace will be talking about the methods we used. James will then talk about the results we obtained before Ashley gives us a discussion about them. Cee-Jay will then follow up with information about how this is pertinent to management of land. So first, what is erosion? Erosion occurs as part of a natural weathering process, caused by the movement of wind or water over the surface of the land. Erosion can cause the loss of fertile topsoil, resulting in a profile that cannot host flora, leading to a positive feedback cycle of increased erosion, such as a dust bowl in the American Midwest. Erosion via rainfall can cause significant problems with the formation of gullies and potential transport of contaminants. The runoff sediment can be transported into streams, increasing turbidity and altering aquatic ecology. Rainfall-driven erosion was the focus of our experiment. Ecological restoration is the final stage in the mining process. The ultimate goal of restoration is to return the degraded land to its prior self-sustaining biodiversity and functionality. To reduce acid mine drainage and other contaminations, evapotranspiration covers are created over the waste rock. However, erosion of these evapotranspiration covers can have detrimental effects on its efficacy, rendering it useless and potentially exposing the environment to contaminants. Since erosion can have devastating effects both financially and environmentally, it's a phenomena that has been extensively studied. In 1976, Yaviv classified the 3 stages of rain erosion. The first stage occurs when the soil is dry and particle detachments result from the collisions of rain, separating lighter particles from heavier ones. The second stage occurs when the soil is fluidized and the rain impacts with the fluidized soil, causing movement. The surface tension of a liquid has been shown to be influenced by impurities, increasing erosion risk in things like sodic soils. The third stage occurs when overland flow is formed, either through the saturation or infiltration excess. The force of the flowing water shears away the topsoil from the surface, transporting it elsewhere. So with this experiment, what were we trying to do? This experiment aimed to quantify the rate of soil erosion and how it differed when soil was exposed to different rainfall intensities. By simulating rainfall over trays of soil and measuring the movement of sediment, the rate of erosion for the soil type and slope could be quantified. We wanted to be able to use this information to work out how management of mine closures or rehabilitation projects could be affected by rates of erosion. Our hypothesis for this experiment was that as the intensity of rain increases, the transport of sediment will also increase as a result of the increased splash erosion and runoff. Now I'm going to pass you on to Grace, who'll talk about the methods. Thank you.
To simulate erosion using a physical model, this experiment used a high-pressure rainfall generator, shown here in this image. This consists of 3 trays which hold soil and a raised sprinkler system placed above the trays. The 3 trays each measured just over half a metre squared or 550 centimetres squared and were raised on one side to create a 30-degree incline representing a hill slope. Each tray had a topsoil that was 10 centimetres deep, made of Pilbara soil that contained some rocks and gravel. This was compacted by hand and made to be level with the rim of the trays to allow free runoff of water. The material under the topsoil that filled the bottom of the trays was river sand. Once the trays were prepared, the sprinklers which simulated rainfall were turned on. The first measurements of sediment began as soon as runoff was visible from the trays. Sediment measurements were performed by collecting runoff in a container for a period of 30 seconds. This was repeated 15 times with an interval of 3 minutes between the removal of one container and the placement of the next, and was done simultaneously for all 3 trays. Measurements of rainfall were also collected in a similar fashion by placing containers randomly under the sprinkler system in front of the trays. Rainfall collection buckets are visible in this picture. In the first week, rainfall collection containers were left under the sprinklers for approximately 15 minutes, and in the second week, this was reduced to 10 minutes to allow for the increased rainfall frequency. The rainfall intensity remained relatively constant over the 2 weeks, however the rainfall frequency was changed as this was variable being tested. This was achieved by decreasing the intervals between each rainfall generation. In the first week, rainfall was generated every 10 seconds, and in the second week, rainfall frequency was increased and generated every 3 seconds. All the samples taken from both weeks were weighed, taking into account the weight of the containers prior to being filled. Samples of runoff were then oven dried and reweighed to measure the amount of sediment removed from the soil. Rainfall data was also calculated and converted to a rate of centimetres per hour for both the first and second week. Data for runoff and sediment also had to be converted into appropriate units of measurement prior to analysis. Water runoff was converted into millimetres per metre squared per minute, and sediment was converted into grams per metre squared per minute. Observations were then plotted over time. Using this data, infiltration rate for each tray was also calculated. A two-tailed t-test, assuming equal variance, was performed between the erosion rates of the first and second week to determine whether there was significant statistical difference between the two.
Within the first experiment, it took approximately 5 minutes for any runoff to be produced after the rainfall generator had been turned on and time had started to be recorded. Once runoff had started to be measured, we saw that there was quite a large variation between trays. Trays A and C, which were on either end of the rainfall generator, were experiencing more runoff and had a larger sediment flux than tray B. Further, the sediment flux was initially quite responsive to increases or decreases within the runoff flux. This is particularly evident 20 minutes into the experiment for trays A and B, where a substantial increase in runoff generated led to a proportional increase in the sediment flux. As the experiment progressed, this relationship started to weaken as the sediment flux became less variable and less responsive to changes within runoff. This was particularly evident in tray B, where a significant increase in the runoff flux 52 minutes into the experiment didn't increase the sediment flux, which actually continued to decrease. Runoff was generated within the first minute of turning the rainfall generator on for our second experiment. Results from this experiment were substantially different to those found within the first experiment. The increase in rainfall intensity was evident as the average runoff flux went from 298 millilitres per metre squared per minute to 1,639 millilitres per metre squared per minute. There was also a substantially higher sediment flux, with less variation for all trays than that found in Experiment 1. While there was less variation, the sediment flux gradually decreased through the experiment, while the runoff flux increased slightly. A two-tailed t-test, which assumed equal variance, was conducted between the average runoff and sediment flux from each experiment. What we found through this t-test is that the results from these two experiments were significantly different and had no similarities. This was already assumed as the runoff flux was highly variable in the first experiment in comparison to that within the second experiment. It is believed that the initial soil moisture content of the Pilbara soils within the trays had a substantial impact on the amount of runoff generated. I would now like to hand over to Ashley, who will talk to you in more detail about the importance of these results.
For both rainfall simulations, the rate of runoff was much higher than the rate of sediment transport. This is to be expected as the generation of runoff is the main mechanism that transports sediment down the 30-degree incline. When frequency of rainfall was set at 10-second intervals, both erosion and runoff showed a general trend of significant increases around the 5 to 6 minute mark. This was followed by significant decreases and then a plateau. This is due to soil armouring, in which the unstable, fine-grained particles are removed first, leaving behind only the stable, coarse-grained particles. These are much harder to remove. The spike in runoff was likely due to Hortonian or infiltration excess runoff, as a result of high rainfall intensity. The plateau in runoff is likely due to the soil reaching saturation, resulting in a steadier runoff rate. When the rainfall was set to a frequency of every 3 seconds, a significantly higher rate of runoff and erosion were observed and at a much earlier time. This is because there is an increased volume of water entering the soil in the same time frame. This means that the soil would reach saturation much earlier. The erosion is also higher due to the increased number of times rainfall impacted the soil. This increased splash erosion. Erosion also increases as a function of increased rainfall. The results for this simulation were much steadier. This could be due to the soil reaching saturation much quicker. It is also likely that the soil was already saturated due to the trays not being emptied or drained prior to the second trial. Infiltration was recorded at a much lower and even negative at points during the second scenario. This is suggesting that the runoff is higher than rainfall, which would only occur if there was a second source of water coming from the catchment. This may also be as a result of the soil not being drained or replaced following the first experiment. As previously mentioned, the soil was not drained before the second trial. This is a limitation to the experiment since both trials began with differing initial soil conditions, for example saturation levels. This results in less infiltration and significantly more saturation excess runoff in the second trial. This would mean that the comparison between both trials are not reliable, though it does allow for an understanding of the patterns in sediment transport and runoff in both saturated and unsaturated soils over time. The 3 trials for runoff and erosion under each rainfall frequency were not averaged because data from each tray showed to have different results, particularly during the first simulation. This could possibly be due to uneven rainfall distributed by the rainfall generator, in which case more trials should be included to mitigate differing results. Another reason could be due to inefficient or different measurement techniques, as the experiment was conducted by a large number of people. These experiments could be conducted by less people in future.
This study allowed us to see that varying rainfall intensity has a substantial impact on sediment transport and runoff. Studies conducted on these factors and the way that they influence erosion have numerous management implications across a broad variety of sectors. These effects are likely to be particularly noticeable in the development of soil covers for land rehabilitation over toxic soil such as those found in mine sites and landfills, as well as developing sustainable agricultural practices and in urban planning projects. Soil covers are used to prevent infiltration from reaching toxic soil that can cause damage if allowed to leach from their containment site. Erosive processes are particularly prominent during the first few years of a soil cover's implementation, when vegetation communities are still developing. Erosion removes topsoil, which not only thins the cover, but depletes valuable nutrient stores and hinders plant growth. This prevents soil covers from being effective and may allow water to reach toxic soils, resulting in leaching. Knowledge of sediment transfer and runoff potential in different soil covers can aid in choosing the most efficient cover and protecting the cover once it is installed. Erosion may be prominent in land used for agriculture, as the land is often stripped of native vegetation and replaced with shallow rooting crops that do not hold soil in place, or with livestock that change nutrient distribution and compact soil. Understanding different rainfall intensity impact on sediment transfer can allow farmers to plan cropping and livestock locations in ways that are least affected by heavy rainfall events. Heavy rainfall events must also be considered during urban planning schemes to prevent damage to property and dangerous events such as flooding and landslides. Understanding erosive processes in areas where buildings are being constructed allows for appropriate drainage systems to be installed. Assessing the impact of the heaviest rainfall frequently experienced by a developing area ensures that the drainage system can handle relatively larger runoff and sediment loading whilst remaining within the smallest possible budget. It can also allow for improved water quality and prevent building around areas with excessive erosion rates that may result in catastrophes such as landslides. Further studies may focus on the impact of hill slope and topography on sediment transport and runoff generation. The angle of the slope will impact the way sediment is transported, as well as how water flows both over and through the soil. The shape of the hill slope will also influence these things. Furthermore, topography may influence sediment transport and runoff tendencies, as the large rocks on top of the soil in our experiment were impervious to rainfall, thereby protecting the soil underneath. Different soil types would also change sediment transport and runoff, and how these are impacted by changes in rainfall intensity.